is now starting. All attendees are in listen-only mode.
Hey everyone, thanks for joining me for this session. I'm Alok Srivastav. I work for Red Hat as a technical product manager. I'm responsible for all the downstream releases of Red Hat cluster storage. I joined Red Hat around 3 years back and it has been a great journey so far. I've spent more than a decade in the storage industry across traditional players as well as startups. And I'm pretty sure that most of you would have heard about containers, and some of you may have been working on it as well. So there is a lot of buzz around containers, not only within Red Hat, but across the industry in general. So what is it? What is it about containers which is getting everyone interested? What is it about containers which is getting everyone excited about it? And what can we do from storage perspective to make containers more interesting? So in this session, I will introduce the idea of why we need container technology, which pain point it solves, how Red Hat is enabling container technology, and we will also talk about the need for persistent storage. So what are containers and why do we need them? By definition, containers are a software packaging concept that includes an application and all of the runtime dependencies which you need to get the application up and running. Now look on the image, the graphic on the left-hand side of the screen. Now it shows a server with operating system installed on it, and then you can have multiple containers running on it. Now does it ring a bell? Does it make you think that containers are similar to virtual machines where you can have multiple VMs running on a physical host or a server? Let me tell you, the similarity ends there. So how are containers different from virtual machines? Now, with containers, you abstract the operating system kernel, while with virtual machines, you emulate the hardware, and then every virtual machine which you create gets its own operating system. Talking more about differentiation, containers are available only on Linux platform, whereas if you have any hypervisor, you install the hypervisor on a host or a server, and then you can create virtual machines with almost any supported guest operating systems. Now, look at the image on the right-hand side. So if you look at the virtual machine model, there is a hypervisor layer. Then you will create multiple virtual machines, and each virtual machine will have its own guest operating system. Each guest operating system has its own applications and dependent libraries. Now, if you look at the containers image, there is no hypervisor layer here. There is no guest operating system layer here. And lack of these additional overheads, if I may call them, so lack of these additional overheads makes container more efficient. So what's the big deal? What's the big deal with containers when you can deploy your applications on bare metal servers, or you can even deploy them on virtual machines? Let me tell you, time to deploy is a big differentiator, and how many applications you can deploy, how quickly, is a big differentiator. So while you can have only one application instance per bare metal, and maybe you can have 10 to 100 applications per virtual machine, but on the same time you can have hundreds and even up to thousands of applications with containers. So here I'm emphasizing on it again. With virtual machines, you need a guest operating system on every virtual machine, and the applications run inside these virtual machines. But containers are a whole new ball game. Unlike virtual machines, you skip the overhead of running an entire guest operating system for every application environment. There is also no need to provision a whole new machine to have a place to deploy, which means that you can spin up or you can scale your application with much more efficiency, speed, and accuracy. So to summarize, unlike virtual machines or physical servers that require spatial attention, containers can be spun up, can be replicated, can be destroyed, and can be managed with much greater flexibility. In fact, as you can see here, the deployment time goes from days with bare metal to hours with virtual machines to minutes with containers. Now, if you look at the flow at a very high level, this is how it all works. You build a containerized application, you push the containerized application image to the container registry. Now, these containerized images are pulled into the test or production environment, and it all takes a few one-line commands to do all of it. So it's very easy, right? So you can use Docker pull to pull the image. You can run Docker run to run that image. Now let's say, for example, if you have a container registry on Red Hat portal, so you can use these commands, as I mentioned, Docker pull to pull the containerized Red Hat storage image maybe on your machine, and then you can use Docker run to spin a container. So before we delve deeper into persistent storage for containers, etc., let's spend some time in trying to understand the software-defined storage concepts. And I will also spend some time on explaining Red Hat cluster storage, as it will help you to get a better grasp of things as we move forward in this session. And so as you're seeing here, there has been an evolution in the way we created software. So we have moved from waterfall to agile to DevOps, and there has been an evolution in the way we provision systems from bare metal to virtual machine to containers, and even your infrastructure has moved from enterprise data centers to cloud. And similarly, your storage systems need to evolve. Your storage systems need to evolve to manage today's workloads, today's infrastructure, and today's development model. So let's take a look at, let's spend some time on understanding the difference between traditional monolithic storage systems and open SDS systems. Now if you have monolithic systems with proprietary hardware and software, so each of these storage systems support limited capacity and performance. So let's say if you have a traditional storage appliance, monolithic appliance, hosting several applications which need more capacity, and the capacity may also max out. So you can add certain number of disks, and after reaching the point where you hit the limits of maximum capacity supported by the traditional appliance, you need to invest in new set of controllers with disk shelves. Now, likewise, if you look at performance, then CPU or memory may also max out, and then you need to invest in additional storage monolithic appliance. So you cannot simply aggregate the capacity and performance of appliance 1 with appliance 2. Now, on your screen, if you look at the right-hand side, we are talking about a solution where you can have industry standard x86 servers. You can install open software solutions like Gluster or Ceph, and these servers get converted into storage nodes, and then you can add n number of such nodes together, which means that you can scale linearly in terms of both performance as well as capacity. Now, in spite of all the great stuff that we talked about SDS and where it fits in, so there are certain workloads and use cases where traditional appliance, if I may use the word AIO, all-in-one model, fits in very well. So if you are looking for a small scale and maybe few terabytes of capacities, traditional storage will meet your requirements, it will suit your requirements, but then you will not get benefits of true shared nothing scale out systems. Whereas with open SDS, with open software defined storage, you get benefits of scale and lots of flexibility for obvious reasons. I've used this term SDS multiple times in the talk so far. So what exactly is software-defined storage? Software-defined storage is server-based storage. You can have storage software installed just like an operating system on standard x86 servers, right? And then you can aggregate capacity and performance, and then you can provision data services to multiple users or applications from the cluster of x86 servers which have this software-defined storage running on top of it, right? So what else is software-defined storage? Centralized control and orchestration. So centralized control and orchestration is all about provisioning, allocation, deallocation, and all the regular storage administration tasks. So let's say, for example, if you have heterogeneous storage systems, so one form of software-defined storage can also be a unified software which does installation, configuration, and dynamic provisioning all from a single management user interface. What else is software-defined storage? Open source. Red Hat, as you know, Red Hat as a company has an upstream first philosophy. It means that every single line of code goes upstream first before people like me, before product managers like me, productize the feature set and ship a downstream product. So, for example, if you see both Red Hat Ceph storage and Red Hat cluster storage are also based on upstream Ceph and cluster projects. So, it's important to get this right. So let's spend some time here to understand what's cluster storage and how it works. Gluster is an open source based software-defined storage, and it is used primarily for storing petabytes of unstructured data. Now, when I say unstructured data, I'm referring to the data which cannot be entered in an Excel sheet. And some of the main use cases of Gluster include storing media and video files, documents which again can be large or small files, and geospatial data, and persistent storage for containers. So let's look at the basic components of Gluster, and it's very important to understand them as these are the most frequently used terms when or as and when you will explore Gluster. So on this screen, look from the right hand side to the left. Now, you will install Gluster on a standard server, just like a regular operating system is installed. Now, that server, that x86 server, gets converted into a storage node. Now, this storage node will have some internal disk, right? Some internal storage in the form of 7.2K RPM disk or any other RPM disk, right? So you will create bricks on those internal disks, and each brick is an export directory on a server, and the data doesn't get stored on the nodes. The data gets stored on the bricks, right? And how you express a brick? So a brick gets expressed by combining a server with an export directory. So, for example, your host name /exports/ your export directory, right? So that's how you express a brick. And then you will create similar bricks on every node which is part of the Gluster cluster. Coming to volume will span across multiple bricks on multiple nodes, and volume is what you mount on the clients, and the clients which have applications which will access storage, right? Take a look at the elastic hash algorithm, which is the heart of Gluster. So this elastic hash algorithm decides where exactly a file will reside, and it also enables the clients to know the location of a file, so that clients can perform the I/O operations as and when needed. Having a look at the cluster architecture, so let's say you have n number of servers on which cluster is installed, right? And these servers are all aggregated, and the storage, the aggregated storage capacity can be accessed by clients. It can be either via Fuse or SMB or NFS protocols. Now, keep in mind that Fuse client access is with cluster is highly available by default. So if you just use mount-t cluster FS a volume name on a mount point, then any cluster node can go down and failover will happen by default. Failover will happen automatically. Now, however, if you are using SMB, sorry, if you are using SMB or NFS, you need to configure additional clustering mechanism. Let's take a look at let's take a quick look at the volume types. So distributed is the default volume type in cluster, and distributed volume doesn't offer any kind of failure protection. So you can think that it is loosely similar to RAID 0. Next one is replicated, and as the name suggests, this volume will keep a copy of the file on a different brick, preferably on a different node, and it's loosely similar to RAID 1. The third and most often used volume type is distributed replicated. Now distributed replicated volume type is again loosely similar to RAID 10 or RAID 10 as it is called, and this volume type offers huge scalability to the replicated volumes. So if you see here, Gluster is the core of container native storage, and we will talk more about it, we'll discuss more about it later in this session, right? And just to talk about some of the features, so Gluster supports another volume type apart from the three that we talked about earlier. So it supports a third volume type known as dispersed, and then there is a distributed dispersed volume type as well. So these volume types are based on Reed-Solomon erasure coding. So with erasure coding, you can sustain failure of 2, 3, or even up to 4 nodes or bricks. Now, if you look at replica 3 and compare it with erasure coding, now so with replica 3, you invest in up to 200% extra storage space. Now with an 8+3 erasure coding configuration, you get similar redundancy with only around with roughly around 40% extra storage space. Now, so Gluster also has tiering. Now tiering enables files to get promoted and demoted between the hot and cold tiers based on the access frequency. So it means that the hottest files, comparatively hottest files, remain on the expensive flash media, while the cold files reside on the lesser expensive spinning disk. So it also has geo-replication, which is all about asynchronous replication of data between master and slave sites. So these sites, the master and slave sites, are usually geographically apart, and there is significant latency between these sites, which explains for the asynchronous nature of replication. So with this, the data replicates in an async fashion, and there is an incremental replication, which means that only the changes get replicated if for some reason georep gets stopped or paused. Then there is bit rot detection, which takes care of a very peculiar problem, which is known as silent data corruption. Now, at times, some of the bits of the stored data get flipped over a period of time, and it results in data corruption. So Gluster has a bit rot detection daemon. This bit rot detection daemon runs in the background and detects any and it also reports to the storage administrators any silent data corruption, so that the necessary necessary corrective action can be taken. So you can also take point-in-time copies of Gluster volume. So This is the snapshot feature, which helps in restoration to a previous copy of data. And these are space efficient snapshots, which are based on LVM and thin provisioning. And these snapshots are read only. And there is another mechanism with which you can take writable snapshots or clones as well. And then so there are instances, right? So there are instances when you want to limit the amount of storage which can be used by a volume or a directory. So to do that, we have volume and directory level quota, right? So you can set a soft and hard limit on the volume and directories, and the administrator gets a warning when soft limit is crossed, and the writes fail when hard limit is reached. So we also have network encryption, which makes use of TLS SSL, and then there is at-rest encryption, which comes from Red Hat Enterprise Linux's dmcrypt. Another uniqueness of Gluster, another uniqueness is that you can deploy it either on a physical machine or as a virtual machine, or even in public cloud, or even as a container, which is what we will talk about in detail later in this session. Now, so public cloud means that you can run Gluster instances in AWS, Google Cloud, or in Microsoft Azure world, and the feature set which you get with Gluster remains pretty much the same. So why bother? Why should we bother about a Gluster-like solution for containers? What's so special about Gluster storage for containers? Now, to get that, to understand that, let's just try to understand, and some of you may already know it, so it may be a review for most of you, while it may be new for others, right? So let's spend some time understanding stateful versus stateless. So stateless means that there is no memory of the past, and every transaction is performed as if it was being done for the very first time. Now, stateful means that there is memory of the past, and previous transactions are remembered, and the previous transactions may affect the current transaction. So when the work on containers started, when containers started getting adopted, it was all about stateless applications. But if you see in today's world, most of the interesting applications, for example, database or messaging applications, they are all stateful, right? And stateful applications, by definition, when you deploy them as containers, and let's say a container goes down, right? So you want your data to persist when it comes back up, when you spin a new container, right? And Gluster allows you to persist the data, and data resides on the Gluster storage. So even when a Gluster node goes down, when a few Gluster nodes go down, the Gluster volume spans across other Gluster nodes. So there is immense high availability. Now, for the same purpose, you can also use traditional storage system, right? But with the traditional appliance model, you will sooner or later hit the limits, which we talked about earlier. So if you look at Gluster, it is well integrated with Red Hat OpenShift platform. What it means that it is thoroughly tested, generally available, and fully supported by Red Hat. So let's look at some of the statistics. Here's a survey result, right? So in 2015, we got a survey conducted by a Forrester Group. So a good number of decision makers in the IT development and operations were asked. They were asked, where exactly do they think containers will be useful? And most of these applications need some form of storage or other. So let's take a while to understand a Red Hat storage journey of containers. And let me tell you, obviously, it did not happen overnight. So once we had, or only once we had, a feature-rich, rock-solid Gluster storage product, we had container-ready storage in November 2015. That was followed by containerized storage in March this year, and eventually container-native storage in June this year, which was released during Red Hat Summit, right? So let's look at details of what each of these container solution means. Now, container-ready storage is the model where you have storage and containers running independent of each other. Now in this configuration, in container-ready storage model, the Red Hat cluster storage installation, the Red Hat cluster storage software runs in an independent cluster. Now this can be on-premise, or it can be even in one of the supported public clouds like Microsoft Azure, Google Cloud Platform, or even AWS. Now, you can access the storage over the network from a platform like Red Hat OpenShift. And Red Hat OpenShift is optimized to run containerized applications and the related workloads. So Red Hat OpenShift ships with the appropriate cluster storage plugins which are needed to make this configuration work out of the box. And then there is Kubernetes. So Kubernetes is something which does the integration, right? So it is Kubernetes is the main integration point here, and containerized applications get described within Kubernetes pod files, and the storage that is to be mounted into the container for the application to use it also gets described in the pod files. Right. So and these and then there is the Kubernetes volume plugins which ensure that the selected storage, the storage which you have mounted, so it gets mounted successfully into the container. That's what the Kubernetes volume plugins will ensure. So what we did next was more interesting, and so far in this session I've talked about containerized applications. Right, and then cluster as a separate entity. Now, what we did in March this year, in March 2016, we released containerized cluster storage. What it means was that cluster became available as a containerized image in Red Hat Container Registry. So you can pull this containerized cluster image on your Red machine, and then you can run it as a container on your host. Now, coming to container native storage, so you can run containerized Red Hat cluster storage inside. With this model, you can run the RHGS inside Red Hat's OpenShift container platform, and RHGS or Red Hat cluster storage containers are orchestrated again using Kubernetes, just like you will do it with any other application container. So the storage container pools and serves out either local or even direct attached storage from host, and then you can have access to clusters rich set of enterprise class storage features, data services, and even data protection capabilities for both your applications and the microservices running in the OpenShift environment. So with this model, you can choose storage intensive nodes, which means that the host with local or direct attached storage within a cluster, right? And you use those nodes for deploying storage containers. Now these storage containers can even co-locate with application containers. So this container native storage or CNS solution also makes use of a RESTful volume manager, which is known as Hekete. So Hekete does dynamic volume provisioning, and Hekete is something which provides the binding or glue which is needed to manage multiple cluster volumes across the cluster. So it allows Kubernetes to provision storage without it being limited to a single Red Hat cluster storage cluster. So after looking at all the technical details, right? So let's make things a bit easier and understand it in a layman's terms. Now, as you can see on the screen, so when you want to get a car, right, you can very well get it assembled, right? So you can just get the body of the car and all the spare parts, including engine, steering, seats, wheels, etc., and assemble the car. You'll get there for sure, but the cost will be huge. Or you can get a proper car, which you can just drive, because that's the goal, right? Remember, the end goal of getting a car or any vehicle is to commute, and it's not about assembling it. And that's exactly what Red Hat does. It gives you the complete car. It gives you software-defined storage, which is integrated or well integrated with OpenShift, Kubernetes, etc., and it's all supported by Red Hat. Again, Red Hat has been building a rich storage ecosystem, which is around containers, right? So it brings stability, security, and also simplicity, to emphasize on that, right? Also simplicity to this critical area. Now, rather than expecting the organizations to cobble together container environments or even hire significant container expertise, Red Hat's full technology stack approach, which is listed here on the screen, it provides an end-to-end containerized ecosystem. So what is in it for the customers, right? So without naming them, let me tell you that a leading telco who used Red Hat container solution, they were able to ship their solution faster. So their go-to-market was fast. And co-residency of storage and compute, as we talked about earlier. So the co-residency of storage and compute allows for the reduction in overall cost for the obvious reasons. So there is plenty of innovation happening in the community. We have volume drivers not just for Gluster, but also other storage types as well. So it can be EBS or Ceph or any other storage drivers as well. Now, let me do some bragging, if I may use the term. And this is a badge of honor slide for Red Hat Storage. We have been listed as a visionary in the first ever Gartner Magic Quadrant report, also known as MQ report, on distributed storage systems. Again, these are some of the resources. You can go through them. If you have a Red Hat account team member working with you, you can ping them to get more assistance. Once again, thanks a lot for taking time out to listen to this session. Thank you.